Okay, we are working on the second half of section 3.7, which is maximization or minimization problems. This one is we have a minimum length we are trying to find. We have two posts. One of them is 12 feet high and one of them is 28 feet high, and they are 30 feet apart. They are to be stayed by two wires attached to a single stake in the middle, running from ground level to the top of each post. Where should the stake be placed to have at least amount of wire? So we are connected by a wire. Here's the stake in the middle. This is a taller one. This is 28 feet. And this is 12 feet. Now we know that the two posts are 30 feet apart, but we have two different lengths here because we have two different triangles. I'll make the smaller triangle length x, which would make the second triangle 30 minus x, since we know that combined it's going to be 30 feet. And then we have two other measurements, z and y. Now our wire, the total length of the wire is going to be the y plus z in this picture. Now we have two different triangles, so we actually have two different primary equations. The first one is x squared plus 12 squared equals y squared. I need to solve that for y, so we can plug it into the w. Y equals the square root of x squared plus 144. That's going to go up for y. And then the other equation that we have is 30 minus x, quantity squared, plus 28 squared equals z squared, and we need to solve that one for z and put it into w as well. Now I'm going to save us a little bit of time and solve for z. X squared minus 60x plus 1684, and then this square root is going to go in for z. So now our w, the one that we're going to take the derivative of, is the square root of x squared plus 144 plus the square root of x squared minus 60x plus 1684. Now it would only make sense that our x value is somewhere between 0 and 30, since that x is on the bottom of the triangles. See how that makes sense? So when we solve for x here, it's only going to make sense to have it between 0 and 30. All right, now we need to take the derivative of w. It's going to be dw dx. Chain rule both times. Save us a tad bit of time. X over the square root of x squared plus 144 plus x minus 30 over the square root of x squared minus 60x plus 1684. Okay, so we need to maximize this, so we would set the dw dx equal to 0, and the easiest way to do that is to subtract one of those two terms and then cross multiply. So the cross multiplied product is going to look like this: x times x squared minus 60x plus 1684 equals 30 minus x, notice that's switched around because we had to subtract that term, times the square root of x squared plus 144. So our critical values here, and the easiest thing to do for this one, this algebra would just be ridiculous. The easiest thing to do for this one is to graph each one of those and then find the intersection points. Or if you started over here, you could just graph this and find the 0. Our critical point is x equals 9, and we also have negative 22.5. But we know that we can't have the negative 22.5 because we have to have a positive x value. Okay, so the 9 we need to put in for w, making sure that we can solve the x for, okay, we just put the 9 into w right here. W of 9 is 50, so we know that that is our minimum. That was the only critical value that we had. So the wire for our answer should be staked 9 feet from the 12-foot pole, since that's what X stood for essentially in the original. Here's our X. Okay. We have one more problem. We have 4 feet of wire that is used to form a circle and a square. How much of the wire should be used for the square and how much of it should be used for the circle to enclose the maximum total area? So we have a square, which means that all sides are the same. Area is x squared, perimeter is 4x. And we also have a circle. Radius r, the area is pi r squared, and circumference is 2 pi r. We know these things. If we have 4 feet of wire and that's supposed to go, forms a circle and a square, A represents the area of the square plus the area of the circle. Which is x squared plus pi r squared. And then we know we have 4 feet of wire to form it. That would be the perimeter of each. Perimeter of square plus the circumference of circle. So 4 equals 4x plus 2 pi r. This is our secondary equation that we're going to solve to get rid of the r. R is negative 2x plus 2 divided by pi, which is 2 times 1 minus x over pi. And that's what we're going to put in for our r. So we are trying to maximize the total area. So the area is equal to now x squared plus pi times 2 times 1 minus x over pi, quantity squared. Simplify before we take the derivative so it's a little bit easier. When we square it, we get 4 times 1 minus x squared over pi, which is 1 over pi times pi plus 4 times x squared minus 8x plus 4. That's what we're going to take the derivative of. So dA dx is 2x plus 4 over pi times 2 times 1 minus x, which is 2x plus 8 times 1 minus x over pi. The critical value of that is approximately 0.56. So we need to test the critical point, that's the 0.56. We also have to look at the endpoints, which would be 0 and 1. When we test those, we get 1.273. Area 0.56 is 0.56, and the area of 1 is 1. So which one of those is going to give us a maximum? We're looking for the maximum total area. That would be 0. So the max area occurs when x is equal to 0, which we just saw. So that's when all of the wire is used on the circle. And we know that because the circle has the radius, so if x is 0, then everything is on the area of the circle. Okay, now that was the second part of section 3.7, which was optimization problems.